So we're moving into radicals. All right, so if we remember was on the last test, right? We looked at homolytic and heterolytic. So if we take the two electrons and separate those evenly, right? That's a homolytic break. If we think about what's happening with a carbon radical, what we need to think about is, what are we doing as far as its geometry? And this is an sp2 carbon, right? With the radical here, right? We've got the p orbital only has one electron in it. I'm kind of showing it up and down there. Okay, so we do have an sp2, the radical is here. The thing to know about this is that this is an electron poor species. So when we look at the radicals, we need to remember that although they have one electron, they are a little bit poor. Question about 3 points. Yeah, I'll add those. I'll try and get that today. If we look at stability, if we think about the stability based on the fact that this is electron poor, then it's easy to understand that this follows the same trend that we saw with radicals. So as an electron poor species, the tertiary is going to be more stable than the secondary, which is going to be more stable than the primary, which will be more stable than the methyl. So when we're looking at reactivity of radical reactions, we can see that they should follow the same reactivity of stabilization as carbocations. So not going to be identical to those, but we'll favor tertiary over secondary. We'll also have stabilized. So if we have a primary radical here, we can delocalize that radical. Right. So we would have a stabilized secondary, and this one would be allylic. And we could have a benzylic. So we still have, just like with carbocations, we're going to have the stabilized allylic and benzylic reactions. Now, when we covered mechanistic steps like our leaving group, proton transfer, nucleophilic attack, we were really focusing on ionic. So what we're going to do now is look at radical mechanism patterns. Again, this can help if you learn the patterns. Sometimes that'll help you turn it into a verbal. So you can list out a mechanism, either what we see with the radicals as types. So the first one is the homolytic cleavage. Again, if we take, something with a weak bond, usually they can add some type of energy. Right, so H nu, right, that's light. So often radical reactions are propagated or are initiated using light as the energy source. And of course, this is just heat. Most of ionics are heat. Light doesn't do much to them, but light will cause a homolytic. So you'll see light used as an energy source here to get these reactions started. Right, and so homolytic cleavage results in going from no radicals, right, to 2 radicals. And that's going to be an important distinction in a second. Okay, we can have an addition to a pi bond. So, we have a radical, react that with a pi bond. We get our half barbed arrow there. And we can add the X to the double bond. So addition across the pi bond. Notice here that we start with one radical and we end up with one radical. Okay. On the radical, so the radical solvent question, we'll put a little box out here. The most important thing for radicals for solvents is non-reactive. Okay, so we need to avoid any solvents that would react readily with radicals. So they don't have the same stabilization. So a proton, as we'll see in just a second, our next radical reaction, a proton solvent that would stabilize a carbocation would be highly reactive with a radical. So we don't need the same stabilization as we need with our carbocations. So what we're really looking for is non-reactive. And so what that ends up being sometimes is just halogenated solvents. Because if they're already halogenated, we don't have to worry about adding more halogens, right? So they're non-reactive that way. And the other one, surprisingly, is ethers. Ethers tend to work okay here, especially if the ether if you make sure that you run it through a medium that takes care of any oxygenated ether species. Ethers tend to absorb oxygen radicals and they can become explosive. So that's one of the reasons you never use an old bottle of ether, and you never use a bottle of ether that has any kind of white flaking on the top of the lid. That's an indication that you've got peroxides in there, and the peroxides can set off a small explosion, enough to cause, not death, but enough to cause, hand problems. Sorry, didn't need to get into that. But solvent question: you don't want the same solvents as you did before. You want non-reactive solvents. Okay, so our next one after the addition is hydrogen abstraction. This is where product solvents become a problem. So we start with a radical. We have a proton, and in this case, it could be R. But again, they can readily abstract protons. It's one of the major mechanistic steps they have. And so we end up with the XH plus the R radical. Again, if we think about this, we start with one radical. We end with one radical. We can have elimination. Which is the reverse of our addition. All half barbed arrows there, so we get a radical plus then our double bond back. So we look at it, we have a radical, one radical goes to one radical. And then the last in this list of possible, generic mechanistic steps is coupling. In coupling, we have radical reacting with radical. Sometimes referred to as radical coupling. And if we look at our range here, we start with two radicals. and end up with no radicals. Okay, so we have homolytic cleavage, right? Addition of a pi to a pi bond, right? Hydrogen abstraction, elimination, right? Creation of a pi bond, and then coupling reactions. Now in radical mechanisms, you're going to have 3 stages. And again, just general, sometimes there'll be more steps than that, but the 3 stages. You'll have an initiation. You have a propagation. And I'll put use radicals. The book has a more elegant way of saying this, but I think it's a paragraph long. And then propagation, use radicals, and then termination. So if we look at these again very generically, we're going to go through a couple of mechanisms. Oh, did I miss halogen abstraction? Yes, I did miss halogen abstraction. Thank you for catching that. All right. Okay, and another one, halogen extraction. Here we have radical pulling one of the halides off, giving us our X plus X radical. And again, if we look at this, we're starting with 1 radical, going to 1 radical. Thanks for that catch. Yeah. So now let's look at the list. Homolytic, addition of pi bond, hydrogen abstraction, halogen abstraction, elimination, and coupling. And I hope that's my scrolling too fast there didn't cause anybody a headache. All right, so the general radical mechanism, right, is initiation, propagation, and termination. Now, when we look at which of these steps are where, in initiation, we go from no radicals to 2 radicals. In propagation, we go from 1 radical to 1 radical. And then termination, we go from 2 radicals to no radicals. Now, because of the way this works, right, you can't go from 1 radical to no radicals. It's always 2 radicals to no radicals. And so if we look at this kind of outline, that means that the only real initiation step is going to be homolytic cleavage. Now, an initiation step in a mechanism, as we'll see later, may have more than 1 step, right? There may be 2 steps to this, but the initiation will result in 2 radicals, which is going to have to involve a homolytic cleavage. Then if we look at our propagation, which is 1 radical to 1 radical, addition to a pi bond, right, could be a propagation step. Hydrogen abstraction could be a propagation step. Elimination could be a propagation step. And the halogen abstraction could be an propagation step. So often propagation steps are several different things that are occurring, and they're a mixture of all of these 1 radical to 1 radical. When we get to termination, terminate the radicals, then it's just the coupling. So it's all of our termination steps are coupling, 2 radicals coming together to create a bond, right? So when we look at these, initiation is always a homolytic cleavage. Sometimes there's a pre-reaction before the homolytic cleavage. Propagation is going to be a mixture of all of those different steps in there, all the ones that went from 1 radical to 1 radical. And then termination is going to be the coupling. going from 2 radicals to 0 radicals. So all of our radical mechanisms are going to have these 3 big steps, each big 3 kind of categories. And then underneath these for initiation, one is most common, but you may have 2. Propagation, you could have 2, 3, 4 different combinations. And then termination is coupling. Any 2 radicals that come together is a termination step. Okay. Questions about those so far? Elimination may or may not be a spontaneous step. It depends on the bi-bond energy that's being created and the energy of the radical. So we're not going to cover it. There is a portion there that talks about the thermodynamics of the reaction. It depends on the radical stability and the energy savings of creating the bi-bond. So elimination is not always spontaneous. Okay, if we look at the next thing, let's look at chlorination of methane. And that's 1 equivalent, right? We're going to focus on 1 equivalent for this first one. We'll show you what happens when we have more. So the first thing that happens in this mechanism is initiation. Initiation happens by taking chlorine and hitting it with light, and it's usually a UV range light. So under that UV light, right, we get a homolytic cleavage to give us 2 chlorine radicals. Then we go to propagation. So our methane, all of these hydrogens are equivalent. So we get a proton abstraction. Right, so we get a hydrogen abstraction. Sorry, proton's wrong. Hydrogen abstraction. Proton is the H+. And now this is where we form our HCl. And then this can react with Cl2. Right now we get a halogen abstraction. And now notice, right, that we're starting our propagation and ending our propagation with the same halide, the same radical. This is not always the case. There are some propagations where you start with 1 radical, but then you may end up with something a little bit different at the end. But this is the most common, and this is the one that you really that really can give you very high productivity, right? What you're doing in this propagation is you're always thinking propagation. Think about seeds. So we're planting sunflower seeds. You plant a sunflower seed, and that one sunflower seed makes a sunflower, and then that sunflower has a bunch of seeds. And you can take one of those seeds, right, and plant it, and then you get another sunflower seed the next year, and so forth, so on. So the kids are planting sunflower seeds. That's a good example of propagation, right? Whatever you start with is what you'll end up with at the end. And then termination is the last step. And it's most often okay to just show 1 termination, but I'm going to go ahead and show all of the possible terminations that, well, most of the possible terminations I can think of here, right? So we could have had the 2 chlorines as soon as they had popped apart, right? So once we got homolytic cleavage, what if those had reacted together? Then that would have been a termination. We could have had the the reaction of the carbon radical reacting with the chlorine radical. So instead of extracting a halogen, just reacting directly with a halogen. Now this one shows us the product, right? But it's not a propagation. This would be a termination step because there's no other radicals after this. There's no way to continue the process. You also could have had, you know, the two carbon radicals coming together. So all of these are possible terminations. The first one is, it happens pretty readily because the two radicals are in close proximity. So you can kind of think about the initiation and termination of the radicals, but then you hit it with light again, right? So if we then take this and hit it with light, we go back, but it is a termination step because it is two radicals going to zero. The second one, that is a true termination. There's nothing you can do about it. The third one is a termination and it's not going to proceed. What happens in radical reactions is that as these reactions start, they start to react very fast. And so if we think about it, we don't have to have a lot of chlorines initiated to get the reaction to occur. But if we have the reaction and we're hitting it with light and we continue to, we're always going to be creating the initiation. And then what's going to happen is we're going to get this going. And if we get this, and there's a high concentration of Cl2, then we're going to get this product, right? But what happens is as the reaction keeps going and we start running out of reagents, that's when termination starts to be a prominent because we have a lower concentration of Cl2 and we start to get, you know, coupling reactions. And sometimes they'll terminate by reacting with impurities. So if there's impurities in the solvent or impurities in the reagent, you can also have a termination step. Any two radicals that are formed coming back together to stop the reaction. So the kinetics of radical reactions are somewhat unique because you always have potential termination occurring, but you can also have reinitiation occurring throughout the process. Okay. Questions about this one? So initiation, we form two radicals. Propagation, we utilize those radicals. We go from one radical to one radical. The best ones you're going to see are going to start with the same radical and end with the same radical, right? And then termination, any two radicals that come together, and they can be widely different. You could even think about a small trace of this ethane here reacting with a radical, and all of a sudden we have an ethyl radical. Again, if you wanted to identify all of the reagents in a radical reaction, you're going to have a very long thesis termination. Now, if we add excess, right, and let's say what can happen in excess is that we can end up getting turn the corner there. You know, we can end up with the full chlorination. So sometimes you'll actually see this just shown as, you know, the bromide excess. And if you let this continue, right, if you give it enough time, this will be your only product. Okay. So this reaction won't stop at the one, so radicals. Radicals are also, this is important to say, radicals tend to be high energy species. Okay. Now there are some radicals that are more stabilized, but in general, radicals tend to be high energy species. So if the reaction can occur, it's going to occur. That brings up selectivity. So if we want a more selective reaction, we actually want a lower energy reaction. If we, as we increase the energy in a reaction, or we increase the energy of the species reacting, we lose selectivity. So if we think about SN2 versus SN1, if we keep the energy low, we're going to favor SN2, and that's going to give us more of the SN2, and that's can be more selective, right? Stereoselectivity. If we look at SN1, if we really wanted to drive, let's say, a secondary carb substrate to an SN1, we would add a lot of energy, because if without sufficient energy to form the carbocation, then we're probably going to go through an SN2. And so when we go through that carbocation, we kind of lose selectivity. So in these radicals are actually probably one of the best examples of the energy or the stabilization of the radical and the selectivity. So let's say we took a simple propane and, we're going to do halogenation. If we do monochlorination or monobromination, okay, and you'll see that in a lot of problems. What does monochlorination mean? It means I add one chlorine. And why would I specify monochlorination, or let's say we have a problem that says dichlorination? That's because this excess, this is always kind of possible, right? If this forms, why would this not react with a chlorine to form that? And so we can end up getting the dichlorinated and the trichlorinated, even some of the monochlorinated, even if we use one equivalent. Okay, so when we look at these, I'm going to say monochlorination, that helps you out. So if you see that written, monochlorination, monobromination, or dichlorination, dibromination, what they're telling you is just add one. Don't worry about any of the groups that are adding more than one. If it says dichlorination, just add two. Don't worry about any of the groups that add one or three. It's not there to throw you off. It's there to actually help you out. Okay, so if we look at this one, right, and now we do it with chlorine, we see that chlorine forms 60% about of this one and about 40% of this one. Now this makes sense from a standpoint that this is a secondary chloride, right? So that would have come from the secondary carbocation, right? If we look at bromine, in this case, now all of a sudden we get a shift in our selectivity to about 97% of the bromide, the secondary, and 3% of the primary. And this comes from the fact that the energy of the reaction and the opposite of energy, right, is stability, is that the fluorine is going to be more reactive than the chlorine. Chlorine's more reactive than bromine. Stability, the bromide is more stable than the chlorine, more stable than the fluorine. So the bromine has less incentive to react than the chloride or the fluoride. So through experimentation, right, we have this kind of selectivity chart. That's a little fuzzy, but hopefully you can read that one. So we can see here that for a fluoride, which is high energy, right, we get a very low selectivity. In fact, you know, we would barely see any difference between a primary and secondary, and then a very small difference between a secondary and tertiary. When we go from a chlorine, we see that we have a pretty good change from primary to secondary, but then a small change to the tertiary. So this was that 60-40 range. But whenever we go to the bromine, first primary to secondary is pretty big, right? We'd have 82 secondary for every one of the primary. But then when we go to tertiary, we see a huge difference, right? So if we have a tertiary carbon with a hydrogen to abstract on it, bromine is going to favor that really heavily. So when we look at these three, if I wanted to make a primary halide, I would want to use fluorine or chlorine. Now, fluorine we know is problematic because it doesn't like to leave, right? So chlorine would be my choice. So really we're looking at chlorine and bromine. If I wanted a secondary or tertiary halide, then I would pick bromide because it's going to be more selective, right? So because of the low selectivity here, I would put chlorine if I wanted primary. Because of the high selectivity here, I would pick bromine if I wanted a secondary or tertiary. Okay, let's try a couple. Give me the major product. Okay, let's take a look. So in the first one, our major product would be this substitution. In the second one, our major product would be this one. Now, let's explain this. So one of the things when I said ratio of hydrogens here versus the halogen, we can use these numbers up here to help us consider this. So if we look at our first species over here, we've got CH3, 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 and 1. So if we look at our primary carbons, how many carbons do we have? We have 9 hydrogens, right? That's 9 hydrogens that could be substituted. If we look at our tertiary carbon, right, we only have 1 hydrogen. If we look for chlorine, we have a 1, right, to 5.1 ratio from our chart. We can, to get us a relative number, right, this is a relative number. For primary carbons, we can take the 9 times the 1, right, to get 9, and we can take the tertiary times the 1 times 5.1. And from this, we can see that this is going to be our major product, right? So we can use this. Now, why does this work? Well, the selectivity between the chlorine on primary and tertiary is 1 to 5. So tertiary is still favored. But if we look at hydrogen abstraction, we have a statistical difference between 9 hydrogens for the primary and 1 hydrogen for the tertiary. So even though tertiary is more reactive, we have a higher statistical chance of abstracting the hydrogens And since the difference between the chlorine primary and the chlorine tertiary is low, that means the primary becomes the major product here. So in this one, it's due to the low selectivity between primary and tertiary, and it's due to the high ratio of primary hydrogens. If we look at the other species, the bromide, now we're looking at, you know, hydrogen, hydrogen, 2 hydrogens here, CH3, 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 okay? And if we look at our primary carbons, right, we have, what is that, 12 hydrogens. If we look at our secondary carbons, I have 2 hydrogens, right? And the molecule symmetric, that's why I can add these all up. And then for my tertiary carbons, right, I have 2 hydrogens. But this is a bromine, right? So if we look at our bromine ratios, what do I need? Do I need to know the exact numbers? Not really, because I just need to know it's really big, right? So I have 1, 82, and 1600. In this case, in the bromide case, is the 12, 2, and 2 really going to make a huge difference? No, right? Because in this case, this is so much bigger than the rest. It's so selective that the tertiary is going to be my favorite product. So with chlorine, the ratio, the statistics of my hydrogens, the number of hydrogens, and the change in the selectivity can determine whether something is going to be favored or major product. But when we're dealing with bromine, there's such a big difference between each of these numbers that you would have to have 82 primary hydrogens to outweigh 1 hydrogen, secondary hydrogen. That's incredibly unlikely. In fact, it doesn't exist. And then if we look at the tertiary, again, your ratios hydrogens really aren't going to play, because you'd have to have 1600 primary hydrogens to statistically overcome the selectivity. So therefore, when you're talking about bromine, it's pretty straightforward. Tertiary, more than secondary, more than primary. When you're dealing with chlorine or fluorine, but chlorine is the one that you're going to see more often, you need to think about both, you know, your ratio of your hydrogens and your selectivity to figure out what your major is. Questions about this? Okay, so we looked at selectivity, and that has to do with regioselectivity, the reactivity of the thing. So let's look at stereochemistry. So if we look at this reaction, right, where we're going to end up is we've got the chlorine to chlorine. We form the radical. And we're going to focus for stereochemistry on this one. So that gives us our 2 radicals. This would be known as the initiation step. Right, then we go to propagation. Here we have the chlorine radical will react with the secondary in this case. So we get a hydrogen abstraction. Now that radical here, right, that's going to be yeah, 3D drawing. So not always fun. Okay, so we could have the radical above, right? Or we could have the radical below. Now, this is not a bond to a atom, right? So this is electron. So this can go back and forth without any problems, right? This is just an electron, and which side that electron is going to be on, right? So therefore, if we take this electron and we react it here to do a halogen abstraction, the second step, then this is going to give me my chlorine on the front. And if I take the other one, oops, one electron arrow. Okay. To give this species, right? And then in this case, get the chlorine going back. And because this can go back and forth, this is racemic. So the stereochemistry or stereocontrol of radical reactions is going to be very similar to carbocations, right? It's sp2. In carbocations, they're both empty, but here we have one electron. That one electron can be on any side of that p orbital, and it can go back and forth. And so we're going to end up with a racemic mixture. There are some radicals that are stereocontrolled, but in enzymatic species. So you can have biological controlled radical reactions that have stereoselectivity, but that's because they are in a three-dimensional cage. So you're bringing in your substrate, you're bringing in the radical, and they have to add in a three-dimensional picture, right? There's no way to do that. If you're doing just solution, the stereo control for radical reactions is racemic. There's no control. Okay. All right, questions so far? I've gone through a lot of radicals today. All right, let's look at one more before we let y'all head to the weekend. Okay, allylic bromination. Okay, if we take bromine and H, we will get the allylic, but the bromine also, right? If we think about bromine is going to be in solution, and that bromine can react to give us this bromination, right? And so we're going to have competitive processes. And the reason for this is that bromine, oops, let me draw that a little better. We often think about these reactions as all the bromine gets radiated at exactly the same time. Well, that's not going to occur, right? If we think about the way reactions really occur, is that they happen to occur like in ionic. It's usually when the reactions happen to run into each other in the solution. It's not like we've got them all lined up and then we hit one domino and it all goes, right? They're randomly going around. Here, the bromide is going to turn into the radical and start the process when the bromide has absorbed enough light energy, in this case, or heat energy, if I had put delta there, to become the homolytic breakage, right? So therefore, there's always going to be bromine, and there will be bromine turning into the bromide radical. And so there, because of the concentration of this substrate, right, this concentration of the bromide, drives the addition. So what I'd like to do is find a way to do this reaction and always keep the concentration of the Br2 low. So I want to have a process where I can end up getting this allylic bromination, or benzylic, as we'll see in a second, without ever having a high concentration of the Br2. So for that, what we use is a reagent that will give me Br2 in situ, and in situ just means in the solution. So I'm not adding it, I am creating it. So we're going to add NBS, and we can use light or heat, and that will give us our benzylic reaction, our allylic reaction, sorry, without the competition. NBS is this molecule, N-bromosuccinimide. What happens in the initiation step? So light, or we could use heat. This one works either way. We get a homolytic cleavage. Okay. Remember, bromide radicals are more stable, so therefore they are selective. So if we have an allylic or a benzylic, that's where they're going to react, because allylic and benzylic is more stable. So bromine radicals being very selective. We get a hydrogen abstraction. Now, at this point, we have a secondary reaction, right? So this is propagation, right? But this is reagent creation or reagent formation, which is that if you take NBS and bromide, HBr, the HBr that's just been made, I get an ionic reaction, not a radical, but ionic reaction to create the protonated succinimide, right? This compound plus then Br2. It's the Br2 that then reacts with the radical. So I'm creating the Br2 in situ. I don't have a lot of it around, so I don't have to worry about it reacting. And so then I get a halogen abstraction. Plus the Br radical, right? And the Br radical can go off and initiate the reaction. So this is always in low concentration. Okay. This can also work with benzylic positions. Right, with either light or heat. And again, bromine is very stable, so it always gives us the most stable, which would be the benzylic, right? So here we can get the benzylic. Now, we don't have to worry about Br2 reacting with benzene, but NBS is easier to work with. NBS, bromine, if you drop a bottle and it goes gaseous, you've got to leave the space, and so it's a little bit more hazardous. NBS is nice crystalline. I used to do this reaction all the time. It's an easy reaction to do. You just measure out your little fine crystals and you put them in there, and the reaction goes. Versus trying to work with a hazardous liquid that if you have your skin too close to it and warm it up, it turns to a gas. So that is our allylic and benzylic brominations.